Well, we're going to run through an example here of how the motion analysis capability in SolidWorks can give us some rather interesting and powerful engineering estimates for the operation of the devices that we design. So returning to the example of the clamp, we're going to see what the force amplification of the clamp is at a particular operating point, at a nominal operating point, which is to say, if we apply a certain force at the input, if you will, what will be this exerting force at the point of application of the clamp when it's in its horizontal position, just as you would expect to use the clamp. Okay. So first of all, here in the model, what I did is I added a post in here, which is attached to the base of the clamp. Okay, so this is sort of an artificial component that I've added in there just for purposes of illustrating when the clamp would be coming to its end of travel. Now, there's no way with the mates other than distance mates to give awareness of the clamp that there's interference about to happen between the components at the mate level, okay, at the assembly creation level. But this is something that we can in fact do at the motion analysis level. And this is when you have the highest level of simulation capability for rigid body mechanics, which is to say, again, motion analysis versus basic motion or animation. Okay, so we'll come here to the tab for motion study, and a few things we're going to do. So first of all, we are going to apply a contact condition between the two parts that we don't, where we don't want any interference to be allowed. Okay, so we have the toggle there selected by default, so I'll click that out, and I'll say that I do not want any interference possible between that component of the toggle there and the base. Okay, so we'll just click OK for that. Okay, we've created, as usual, a default animation of 7 seconds, considering that condition. We're also going to apply gravity here, so we'll turn on that apple, and my gravity is pointing in the right direction here. Okay, so along the y-axis, and then of course in the negative, being the direction of gravity. Next thing we're going to do, and I should have done this already, so instead of animation, we need to turn in fact, here at the add-ins, okay, turn on SolidWorks Motion. Again, if you have that available, that's a component of SolidWorks Premium. And there it is. Okay. We also have so we have gravity. One of the things that I want to do, this force may have been from a previous exercise, but that is in fact what I want to do next. Okay, I want to apply a force in here, and of course the force I want to have applied at the surface of the push button in there. So I'll select that. Okay, and then of course reverse direction, and I want that force to be relative to the component. Okay, so for the component I'll select that same component so that my force remains normal throughout the range of motion of the part. Okay, we're going to apply a force here just to have a nominal number of 100 pounds. And now we have then gravity. If we look here at our tree, we have a particular contact defined between the two bodies and then a force. Okay, and again, I think this was from a previous exercise, so we'll get rid of that. Okay, now let's go ahead and edit the contact features in here, and we have drive rubber. We're going to use that just for purposes of the simulation. Okay, and we'll work with a restitution coefficient, as defined by that particular material. Notice again, this material is independent of the material chosen for the part. This is only for the contact characteristics. And, here the other options that we could have selected. Okay. So with all these components, I'll say yes. The next thing I want to do is modulate my force so that I don't have a step input in the force. So under these conditions, if I just specify a force of 100 pounds as constant, okay, basically what's going to happen is that at time zero, 100 pounds are going to be applied. That's really an unrealistic use of the clamp. I mean, typically we would be increasing up to that force over a period of time. So this is a zero dynamics type of situation, which lends itself to numerical instability. Okay, so instead of constant, what we're going to do is select segments. We're going to edit the segments here and create a table of values of force, with a particular time involved. Okay, so we'll progress from 0 to 100 pounds over the span of 1 second, and then we'll hold it at 100 over the span of an additional second. Okay, the segment type, here cubic, will give us the progression between the starting point and the initial point. Okay, so you can see there that it comes up nicely from 0 to 100 pounds, and then it holds at 100. And then towards the end there, the clamp should have stabilized, and we should be able to read a constant, or rather a contact force at our point of application, the exerting force, and then find out how much higher than the 100 pounds that is. Okay, so I'll click OK and run my simulation. Okay, so we see, if you noticed in there, there's a little bit of bounce, and that's an artifice of the rubber. And then after 2 seconds, the force ceases to be applied. And basically, at this point, we don't need to compute the simulation any longer. In fact, it would be better to just go ahead and recalculate the simulation for only 2 seconds. So in fact, I'll do that again. So recalculating over 2 seconds here. Okay, so we saw a little bit of bounce in there for the rubber. Here at 1 second, the applying force has stabilized at 100, and we can, or should be able to see a constant stabilized exerting force, which is what we're looking for. Okay. To look at our results, we just come here to results and plots. And here what we're going to do is look at forces in this case. Okay. We're going to apply, or rather seek, a contact force. Okay. And then for the contact force, we can look at a component. Again, in this case, we'll just look at the magnitude. And here we want to select the two components that come into contact with one another. And I'm going to select this component, and then through the select other, that's sort of my X-ray vision for the selector, I'm going to select the surface here. If you can read in there, it's really what I want is to select the face at the toggle, not the face at the base. Okay, so with that, I've selected my two contact points, click OK, and now I can read the reaction force. Now you notice that there are some unrealistically high numbers in here at the beginning, so we're talking hundreds of thousands of pounds. Probably that has to do with numerical instability caused at the initial point of application, probably very small volume contact between the two bodies. Really what we're looking for in here is the value that has stabilized. Okay. So that can be done just by double clicking on the scale and seeking a more reasonable scale, and instead of letting it auto scale, so instead of scaling to the maximum point, we'll just scale to say 300 pounds. Okay, and taking away or disregarding the transitional forces, which again are going to be subject to numerical instability, we see that the force does in fact stabilize here at some nominal point. Okay, so in fact, if we double click again and we select major and minor units in here that are more reasonable, so let's say that we go every 20 and every 10, there we can see that we are just shy of 260 pounds. Okay, so if we follow the number that stabilizes, right around 260 pounds. So that is our exerting force. Let's see, just for grins, what would have happened if we had selected our solid body contact to be metal instead of rubber. Okay, so we'll do dry steel. And rerun the simulation. Okay, so we saw a little bit less bounce in there. Let's let the simulation run and see how our results compare. Okay, so let's go ahead and take a look again at the plot. Okay. Now for steel, notice that we have a more reasonable, still not endearing numbering here, so still attributable to, again, numerical instability as the volumes come in contact with one another. But of course, the final force should not be affected by the nature of the materials, and it isn't. Okay, so about 260, from which we conclude that the ratio of exerting force to applying force is in the order of 2.6, and that is the result that we were seeking. Now, one additional item here that is well to point out is that you can select the number of frames per second for your simulation. So this, in effect, fixes or limits in some manner the resolution available for the simulation. This is a parameter that's controllable through the Properties tab. So if you come here under Simulation Properties or Motion Study Properties, you'll see that under Motion Analysis, or for that matter, Animation or Basic Motion, you can control the number of frames that are being used per second to calculate the simulation. So of course, fewer frames per second means a coarser simulation, but also one that is more subject to numerical artifacts of the kind, in fact, that we've encountered, with a bounce. Okay, so some of those, will be very difficult to take out, but in this particular case, they were not relevant, really to our study, and we could live with them at no real detriment to us. And in some other cases, it will be important for you to match the resolution properly, and that's why it's ultimately essential, that you do a sanity check on your results, and you fine tune, these different parameters according to the needs of your simulation.